So from 7.4, what we're going to do today is actually, I find this to be pretty interesting. You're going to take problems that don't look necessarily like quadratics and see how they can be quadratics. Okay, see how they can be quadratics. So let's take a quick look, for example. Look at these three problems here, or these three equations. So the goal for us today is to recognize that some problems aren't quadratic by nature, but they can be written as quadratics. So look at the problem here and tell me how these are all the same. How are all three of these equations the same?
The first term, they all have x squared.
Okay, so some x squared in the first term. Good, that's one piece that's similar. Good, what else? I think you're going to go about more. That's definitely one. Yeah, more.
There's like a integer c value.
There's a constant at the end for all of them, I agree. And notice, what about the constant? In all these cases, it's negative 10, right? What's the constant for b in this case? What's the b value in all these cases? 3. 3, 3, 3. A value, 1, 1, 1. So what's the difference in these problems then? Is what's being operated on. Normally, we know x as our variable of interest. But here, the quantity 2x plus 4 is like our x. The quantity 2x plus 4 is like our x. Here, the quantity 2 over x is like our x. The quantity 2 over x takes place of our x. You see what I'm saying? So all of these equations are the same in structure. It's just that our variable that we're solving for, which is normally a linear thing, or just something like x, is now an expression. Right? These are all expressions. They're not just terms by themselves.
Since they all equal 0, does that mean they all equal one another?
Yeah, so what's going to happen here is not they all equal one another, but the roots to the first equation are the same as the roots to the second, which is the same as the roots to the third. But in the second equation, our answer here would say x equals, but here would say 2x plus 4 is equal to something, because we're changing the variable. So I'm going to discuss that. But yes, they would be similar in answers, and then you'd have to vary them at the very last step. Okay, so let's take a look. Let's take a look, for example, and think about what could be useful. It's very useful to sometimes make let statements. So for example, if I did this, if I said the following, let u equal 2 over x. Let u equal 2 over x. What does the third equation then become? From this statement in red alone, what does the third equation become instead now? Isabella, what do you got?
U squared plus 3u minus 10.
Yeah, very good. She's picking up on this right away and recognizing, you know what, this is just like with u substitution with radicals. Sometimes with radicals it was nice to say, let u equal something, and then we'll go back again and fix it. Okay, we also did this with systems of equations. When it was 1 over v plus 1 over u, and we said let x equal 1 over v, let w equal 1 over u, and then we plug those in instead to make it easier. It's the same thing. So I can solve this problem in part 3 by writing it like it is in part 1. Again, the third line here can be written with u's instead of the x parts, and then it becomes the same thing as step 1. Right? Look at this, look at step 1, they're identical. Obviously it's a variable, but they're identical in structure, right? This is u squared plus 3u minus 10, x squared plus 3x minus 10. It's the same thing. So what we can do here is solve for u. And then plug u in right here to get x after. Again, the goal is to find x, not u. So we're introducing what I use the word for a dummy variable. It's not, I don't know this word, it's actually a mathematical term. A dummy variable means a stand-in. Somebody to stand in for you, like for a moment, until you get back. If you've ever been online in a store somewhere, you know you can't get offline, right? If you're waiting for like a new product, like the iPhone to come out, you're waiting outside the store. But somebody could come by and like stand in for you, and then you come back and play later, right? Same thing here. We're currently saying, you know what? I want to deal with x because I've got 2 over x, and it's really annoying and confusing, and it's 2 over something. So you know what? I'm going to call this dummy variable u 2 over x. And I'm going to take the place of 2 over x here and here, and it becomes this. And once you get u, say u is 7, plug a 7 in right here. If that's a 7 and you want x, just flip-flop these. X becomes 2 over 7. So whatever u is goes back into your let statement to get x. So let's see this actually worked out. Let's look at the example to do this. Okay, so what are you going to make u equal to in the first example? It may be obvious to some of you, maybe not obvious. But just look at the example. What do you think u would equal here? Christian?
2x plus 1.
Yeah, it just makes sense logically here because 2x plus 1 appears as a squared term and it also appears as a linear term. Let's write this down. This is the squared term and this is the linear term. When you get something as an expression that appears squared and linear, and then I've got that 21 on the other side as a constant, I can right away define whatever's inside of there as u. So I agree. I agree with Christian in saying that call whatever is squared and linear as your u value. So this equation then becomes the following. Again, whatever was 2x plus 1, replace it with the letter u. Now, some of you are probably asking or thinking, why are we doing this? Why can't we just square what's up here, right? Take a look, FOIL this out, distribute the 4, collect all of your terms. You can do that, absolutely. And by all means, go ahead and do it. It will just take you a while longer. Honestly, it will take a lot longer. Now, there will be some examples where squaring isn't going to help us much, and those come with their fractions also. So this technique is very useful to use. It may not seem as useful in the first example, but it is very useful. Okay? And again, it's a lot of work to square all that out and collect terms. I don't want to do more work. I want to take the easier route. Okay, you guys know me. I'm not lazy, but I'll be honest. I'm a big fan of taking the fastest way to get from A to B, the optimal route. And this is the optimal route in this case. Move the 21 over. What does this factor into?
U minus 7 and U plus 3.
So that makes my u values 7 and negative 3. But again, pause, ask yourself, are we trying to find u? Find u. Where are you? Find you. Trying to find you. And you? Yeah.
So would you have to substitute like U
Into the what? Yeah, into the let statement. Let's take u and plug it in for u in the let statement. So let's take the 7 and plug it in right here. When I plug a 7 in, this becomes 7 equals 2x plus 1. Subtract 1, it makes it a 6. Divide by 2, it makes it x equals 3. There's my first answer. It's a coincidence, by the way, that it came out to be 3 and the other root is negative 3. It's a complete coincidence. So again, we take 7, plug it in up top for u, subtract the 1, it makes that a 6. Divide by 2 and pretty much solve for x. You end up getting x equals 3 here. But then I need to take this value over here and plug it in. Okay, and when I do that, when I plug in the second case, instead of 7 equals 2x plus 1, I now have negative 3 equals 2x plus 1. So this solved, if I move the 1 over, it becomes negative 4. This becomes x equals negative 2. So my two answers for x are negative 2 and positive 3. Again, the value of u, although it helps me to get x, is not what I'm looking for. I'm not trying to find the u values here and here. I am not trying to find these u values. I have to use them to get x later on. Alex, where are your glasses?
Oh, I keep forgetting.
Oh, man. It's gotta hurt. By the end of the day, you do this so much. You know that like squinting causes headaches, right?
Yeah.
Do you ever get headaches when you go home? Do you ever feel? Just be careful, that's all I'm saying. Try to remember your glasses, man. I see you do this right now. Listen to me. I used to do a lot. That's the only reason I know it, honestly. Anyhow, the two answers for you yield two different answers for x. How do I know if I'm right? I can go ahead and plug in the original to check. And this might be one of those cases where you probably, or you want to try checking it in the original statement itself. Okay? Is the process clear? So what's the first step? Somebody summarize this. What's the first step we're going to look for?
You find something to substitute with u.
Good. Find what looks like the dummy expression to replace with u. And in this case, we look for the squared term, we look for the linear term. That repeats itself, so that's got to be u. That's step number 1. What's step number 2? Once the u is in here, what's the second step?
solve it?
Just solve it, and solve it for the variable u. So again, replace the expression with u, solve for the variable u, which is right here. And then the third step, once we have the u values,
Substitute it back into the dummy expression.
good. Plug it back into that let statement, your dummy expression for u. And once you plug each of these separately in, you'll get two answers. When you plug the 7 in for u, you get x equals 3. When you plug a negative 3 in for u, you get x equals negative 2. Okay, so those are my two cases. We're going to do more examples of this, but is this somewhat clear right now? Is this somewhat clear? So, can I make an overarching statement? I can. Look at the linear term. The linear term is pretty much u. The linear term is always going to pretty much do whatever u is. Again, take a look at it. The linear term was 2x plus 1, and we let u equal 2x plus 1. It's very useful to point that out. I know it seems like it's trivial, but right now, it's easy because this problem is easy. I'm going to get to much harder problems in a minute. So the middle term, the linear term, is very useful to designate as u. Okay, it's very useful to designate this middle term up here, whatever it turns out to be, as the u expression. Let's take that concept and carry it in here now. A lot of people in the room would say right away, it's not a quadratic, Mr. Howe. This is definitely not a quadratic. And I would agree if I looked at it quickly. But it is a quadratic. It is. It is a quadratic. What did we say in the last step? If you don't know what to make u, what should we look at? Make it the what term? If you don't know what to do. The linear one. So, you know what? For now, I don't know what to make u. I'm not sure. This looks pretty confusing to me. And to solve this, it would be pretty messy. I'd have to isolate the radical. I'd have to square both sides. I can do this the old school way, which we did. But it's a little bit messy to me. So I'm going to say let u equal radical x. Again, whatever the linear term is. Obviously, the coefficient of negative 7 is there, but I'm not talking about the coefficient. Just the actual variable portion of the linear term. So if that's true, then what's u squared? If that's true, then what is u squared, Eduardo? X. And Eduardo saw that because if you just square both sides, right? You square u, you get u squared. You square radical x, you get x. Well, that's actually pretty useful now, actually, right? When I think about this. Because I've got a radical x somewhere in the equation. I've also got x somewhere in the equation. And that x can be replaced with u squared. So I'm going to go ahead and take now the original equation I had, and I'm going to take these values and plug them in. I'm going to take this u and replace this with it, right here in blue. And then in yellow, I'm going to take u squared and replace this x with it, right there. Again, because that's physically what x is equal to. X is equal to u squared, so I'm going to replace that x with u squared. So the first term becomes 2u squared. The second term becomes minus 7u. And the last term just carries over as a plus 6. I'm trying to do it with colors so you guys can see the association, okay? So the yellow came from the linear term, from the quadratic term. The blue came from the linear term. What I do now, I can factor. That's the reason we're doing this, to show that it's a bit of a simpler way to approach a solution. I'm not even sure if we can factor this. Let's see. Does it factor? It does. What do you got? Anybody have the factors? You got it? Yeah.
X minus 3 and x minus 4.
Careful. Where you're looking at x minus 3 and x minus 4.
Don't you do AC method?
You do. It's got to be a 2 somewhere. Let's start with that. Is that clear?
Oh.
See what I'm saying?
No.
I mean, if I look at this, what multiplies give me something u squared with a 2? It's got to be 2u times u gives me 2u squared, right? So I know already it starts like that. So you can use AC method, really. That's fine. But just be careful. You make a mistake along the way somewhere. It's definitely a 2u and a u. You want to do AC method in case we forgot? You want to show a quick example? So AC method would tell me this. AC is 12 and B is negative 7. What numbers add up to negative 7 and multiply to 12? Now, you were going to ask something else?
Wrong time? Sebastian, what do you got?
4, 3.
Yeah, and specifically?
-4 and
Yeah, -4 and -3. So instead of starting by factoring, if we're not sure how to factor this by just looking, we could start this problem by breaking the middle term into -4u and a -3u. And then we can factor by grouping. Take out a 2u, I'm left with u, I'm left with u minus 2. And here take out a -3 to leave me with u minus 2. And in solving this, u minus 2 is in both terms, that comes out, leaving me behind with 2u minus 3. So that's how I would go about AC method, okay? And I recognize, Julia, because the 2u and the u have to multiply, you need to square it.
I forgot the grouping.
What was your question? What were you going to say? You figure it out? 2u minus 3u minus 2, we got just 2 and 3/2. But again, that's not the end of the problem. It's not the end of the problem. We are trying to figure out what x is. Now, you have two options. You can take the u value and plug it back into here, and then solve for x. Or you can take the u value and plug it back into here, which is more logical in this case, if we're trying to find out what x is. Yeah, the second case just makes more sense. We're not always going to have two let statements. This is one of those cases where we're able to actually show that there are two let statements, or we're able to deduce that. But I would definitely take the 2 and plug it in there, and then take the 3/2 and also plug it in there. When you plug a 2 in, 2 squared is just 4, so x is just equal to 4 from that. So this gives me x equals 4 for the first one. And for the second one, if I square 3/2, I get 9/4. Question is, do both of them work? How will I know if both of them work? How do I know if both of these work? What do I have to do with my answers?
Substitute it back into the original one.
Yeah, gotta go to the originals here. Gotta go to the original. If I plug a 4 in, I'm going to get 8 minus 14 is -6. -6 plus 6 is 0. Okay, so the 4 works. 9/4. 2 times 9/4 is 18/4, which is 4.5. Minus, oh gosh, it's going to be 7 times 3/2, which is going to be 21/2, 11.5. So I've got 4.5 minus 11.5. No, 4.5 minus 10.5, that's 21 over 2, yeah. It'll be 4.5 minus 10.5, and that's -6, and then -6 plus 6 is 0. So both of these are going to work in this case, but I need you to recognize that the original, go back up here, write yourself a note, the original really wasn't a quadratic. If you look at the original, it really wasn't a quadratic to start. We made it into a quadratic, which is what gave us 2 roots, which is what gave us 2 answers for x. So as a result, because we were getting 2 answers for it, we have to recognize that it's 2 answers because it was a quadratic here, yet the beginning wasn't a quadratic. So there's a probability that one of these answers won't work in these problems. So you need to check your answers. You need to check your answers. All right, let's take a look at a trickier one now. We got a couple more. We have 3 more to go. Okay, the next one is not very tricky, but you have to manipulate a little bit. Take a minute or so to take a look at this one to start. Think about how you would make this look a little bit nicer. How would you make this equation look a little bit better and more workable? It's not the right word. More workable. Alex, what do you think?
Could you do multiply everything by 2 or do? Or would you just have one of them equal to 2u?
What are you noticing, Alex? Let's discuss first, because you're on the right track, but you're not saying it right. What are you noticing?
There's 3x and 6x.
Okay, so stop there. It's a 3x and a 6x, and they're clearly not the same, right? For this problem to work,
we have to let u equal one thing. We can't let u equal two different things. So should we let u equal 6x? 6 over x, like we've been saying, the middle term? Or should we let u equal 3 over x, the first term? What do you think?
Let u equal 3 over x.
Why, Alex?
It's just easier to do because you have to square.
It's easier to work with. So if that's the case, how can I rewrite the middle term to make a 3 over x instead of a 6 over x? And just use common sense here. I want to turn 6 over x into 3 over x. So what do I have to take out of it? A 2. So let's rewrite this to start as the following. Oops. I just said it and I didn't do it. Okay? So recognize what I just did. This is what Alex told us. He picked up on the fact that the squared term and the linear term weren't the same. Right? We didn't have the same part there. So let's make them the same. And Alex made a great point. It's really easy to take a 2 out of right here, in the middle. But it's not easy to make this a 6 over x. To make this 6 over x, because it's squared, you can't just double and stuff. It's not easy. So the best root in this problem is exactly what Alex said. And then our let statement becomes simple. Let u equal 3 over x. Because 3 over x appears here, and it appears here. So we can replace in both those spots with the letter u. So 3 over x quantity squared becomes u squared. Plus 2 times the quantity 3 over x, which is really just 2 times u, minus 35 equal to 0. Okay? These are factorable. The later ones are not factorable. We're going to get the ones that can't be factored. I'm trying to make it easy to start. This will factor into u plus 7 and u minus 5. So u is equal to negative 7 or u is equal to positive 5. Am I done? Good, I'm not done. I saw a lot of shaking of heads. No, I'm not. I'm not done because now I need to take those values and plug them into my let statement. I will get 2 parts to this. I can see that negative 7. So again, my let statement is this. Here's my let statement at the very top left. U equals 3 over x. Since u is negative 7, I'll start with that. Let's break this into the 2 cases. Negative 7 equals 3 over x, and 5 equals 3 over x. Those are my 2 scenarios that I'm working with here. And then just solve them. How do I solve this quickly? What's the quick way to solve these kind of problems?
I multiply both sides by 1/3. Is that right?
But then you would get 1 over x on this side, right?
Yeah.
So you'd have to then do the reciprocal of both sides, which works. That's fine, Joey. You can do that. But don't forget, you get 1 over x from that. You got to reciprocate both sides, invert both sides. What's a faster way, Adam? What's a quicker way to do this?
Multiply both sides by x and then divide by negative 7.
Yeah, so look, right here, switch these 2 numbers. It always works. It always works. It always works. D equals RT comes from that concept. You can flip-flop these. It's called the product of the means equals the product of the extremes. Proportionals. Proportions. If we have proportions, you can always flip-flop diagonally. This is a proportion. Negative 7 is really over 1. 5 is really over 1. These are both proportions. You can always switch diagonals in proportions. So this one becomes x equals 3 over negative 7, and this becomes x equals 3 over 5. And there's my 2 answers. 3/5 and negative 3/7. 3/5 and negative 3/7. Now, if you start with an original that's quadratic, you're going to get 2 answers. So you don't have to worry about checking this one. Does that make sense what I'm saying? Go back to the last problem real quick. Swipe back to the last one. The original we started with was not a quadratic. Is that clear? Look at example 2 and look at the original part of example 2. It was with a radical for example 2. We did not have a quadratic there. So we had to check those answers. But here we have a quadratic to start, which means we're going to get how many answers for every quadratic? 2. Always 2 answers. Okay? Questions on example 3? Good. You're already ahead. I can see you on to 4, which is great. That's awesome. So we've done this problem already, right? We've actually done this problem earlier in the year, this exact problem. And a lot of you picked on what we should do earlier in the year. But we could use this concept of U substitution if we want to. I'm going to do it 2 ways. I'll do it the old way we did it, which honestly is faster if you pick up on it.
And then I'll do it with u substitution over here. Okay, the old way we did it was by, just go ahead and solving this by moving the 12 over. And then a lot of you picked up on the fact that this just becomes x squared and x squared. And that was the only difference you picked up on, right? We did this literally already this year. X squared times x squared gives x to the 4th. So it's got to be x squared, right? And then you can figure out the numbers. We could also use u substitution. Let u equal x squared. Right? I could let u equal x squared. And it's usually the middle term. Which makes this equation now, and again, I'll start with this. I'll move the 12 over. But if u is equal to x squared, that becomes a u right there in the middle. Well, if u is x squared, then if I want x to the 4th, I have to square them. This becomes u squared minus 12. And it becomes the same answer in the end. Just with a little extra work. It's going to be a plus 4 and a minus 3, same as over here. So this is going to give us answers of u equals negative 4 and u equals 3. But those are not my answers. I need to take them and plug them back in here for u. So I'll get x squared equals 3 and x squared equals negative 4. Well, look, over here. Solve these. It's the same answer. It's the exact same answer. Solve these on the left. If you solve them, you're going to get x squared equals 3 and x to the 4th equals negative 4, right? By making a t-chart. And then x is equal to plus or minus root 3. And x is equal to plus or minus 2i. And there are my two answers for x right there. So I did this the old school method, where we don't let u substitution work, and we just recognize that since this is to the 4th, this is squared and squared. What if this had been to the 6th? 6th power. Come on.
X cubed.
Then x cubed. 8th power, 4th, 4th. 10th power, 5th, 5th. Is that clear? Right? You picked up on that by now? So we can see for each of these, as long as this is an even number, we'll be fine splitting into 2 there. Yeah?
And so why can't you do, like, put u equals 4, equals negative 4 and solve for x
You
squared?
can. That's what I'm going to do, show in the last step. But we'll get the same answers is what I'm saying. So let's go ahead and plug in that last step. Since u equals negative 4, and u is equal to x squared, we can say, all right, x squared is really negative 4. And x squared is really 3. Right? Because again, I take x squared and plug that back in for u there and there. I can do it that way also. See what I did? I took x squared and plugged it in down here so they can look a little bit easier. But in the end, I get the same answer. Look, right here. This right here is the exact same line as this right here. Right? In black right there is the same thing as in yellow. So you'll get the same answer either way. I'm trying to show you that u substitution is useful, but because there are other ways to solve a problem like this, you can absolutely do it this way or this way. It's up to you. Up to you. It's up to your choice. But if you had a problem like example 2 and example 3, I would absolutely use u substitution. For examples 2 and 3. For 2 and 3. And for the next one, I would as well. So let's jump to example number 5 now. Okay, again, the same answers, right? X equals plus or minus 2i. X equals plus or minus root 3. Exact same answers we got in both cases. Doesn't matter. Example 5, though, is a little bit tricky. What are you thinking for example 5? What do you think for example 5? What should we let u equal? It's not obvious. There's no middle term really here, right? There's no middle term, so it's not useful.
Would you just factor that out?
So one way to do it is to multiply it out, collect terms, and get an answer. Absolutely, Alex. You can definitely do that. But there is a way to make this u substitution. It's a little bit tricky. What if I let u equal what's in the parentheses? Okay? Somewhat reasonable? Okay. Now, if I do that, I need to get a 2x minus 3 as a middle term also. How can I manipulate 19 to make it work so that I can get a 2x minus 3 if I factor something out of here? Look at this as a group. See what I just put a box around? Think about factoring something out of there, but 19 isn't going to work. If 19 changes to something else, it would work nicely.
how will this work? What do you think? I want to get 2x minus 3 out, right? I want to get that out. What do I have to factor out of 10x to get a 2x? Start with that. What do I have to factor out of 10x to get 2x?
5.
5. So can I factor 5 out of 19 though? What can I factor 5 out of to get a 3? What can I factor 5 out of to get a 3?
15.
So I want to make the 19 15, don't I? Wouldn't you agree with that? Is that agreeable? The negative 19, I want it to be negative 15. So watch what I'm going to do. I'm going to rewrite this equation and write it like this. And I'm going to group it like that. It's the same thing. Minus 15 minus 4 is negative 19, isn't it? A negative 15 and a negative 4 is definitely negative 19. I'm doing this on purpose. So now I can factor a 5 out of that middle term. Take a 5 out of here, and it leaves me with 2x minus 3. And although this seems tricky at first, once you pick up on this and once we've done it once, you can kind of figure out the way to process this every time. So if you have a squared term only, you can let that be u, and then figure out how to manipulate your middle term to make it work for this problem. So as a result, this problem turns into the following. That's what this problem turns into. Now again, as Alex said, sometimes if it's a standardized test, if it's the final exam, and you're not told to use U substitution, which you probably wouldn't on any standardized test, I might ask you on my test because I want to see the skill. But if you're just given this problem, it probably would have been better to FOIL it out at the beginning, maybe distribute the 3 and do some work. Okay, before you leave, let me just point one thing out. I do want you to just do the homework on this section. But one thing to point out is that your answers for U will be negative 5 plus or minus root 73 all over 6. That's going to make solving for x a little bit tricky. So please tonight, try to figure out, obviously you can get the u value, use the quadratic formula to get u, but then you got to plug in this whole thing, one with a positive for u, one with a negative for u, and solve for x. It's messy. So if you want to practice this on your own and look through my work and look at the rest of the video, for example 5, I think that would be a useful thing tonight. Yeah? And make sure you keep up your problem set work, please. Problem set work can find pretty quick if you wait.
So you got that by doing quadratic.
Don't worry, quadratic formula, okay? So if your projects are approaching pretty soon, the due date. Look at my schedule, look at your schedule, see when we have free time together. Or maybe like right after school for like a minute or two, and come by there, that's fine. Like right before we have baseball. Yeah, but it's gotta be like right away.
Yeah.
Because I'm late to baseball every day, I'm trying not to be late, but I have to do 10 students come by. I don't want to be students, you know, so it's up. You're welcome.
Also, if I need to, maybe we could just check your schedule.
Yeah, my schedule's on Moodle, so you can see it on Moodle, it's the very top Moodle.
I think your schedule for tomorrow, is that softball count right after school?
Yeah, you want to check the project, so we'll do that. Look at my schedule, it'll take a matter of like 2 minutes if it's right. If it's wrong, I'll tell you what's wrong, and you just assess it yourself. So, if you made a mistake on the bike parts at the beginning, it'll affect other parts. Hopefully, though, your cost, you did formulas for the cost?
I didn't calculate the cost.
Okay, then don't worry. That's a good idea. Some people do the cost and have to recalculate it. But if you do the cost with formulas and then you edit your work, it'll edit the formulas automatically for you.
Maybe I'll do that tonight.
Yeah, you could start doing that. And I would do like the sum of the inventory row times the cost per part at the end. And then if those inventory rows change, it'll change the formula automatically. Okay? You're welcome.
Do you know if we're running today for baseball?
No, we're definitely not running. We are definitely meeting in the gym right after school. The softball's going to start on the roof for their tryouts.
Alright.
So we're going to start in the gym and then maybe progress up to the roof when they're done so we can just finish.
Cool.
Okay?